Hello friends, I welcome you all to this class. This is linear algebra class, and today we'll be solving this example under this theorem we introduced in our previous video, Cayley-Hamilton theorem. And in this example we are told to find a raised to power 4, where a is this 2 by 2 matrix using the Cayley-Hamilton theorem. We know that Cayley-Hamilton theorem states that every square matrix satisfies its own characteristic equation. So for us to use the Cayley-Hamilton theorem to evaluate this a raised to power 4, it is important to compute the characteristic equation of this very matrix, and by Cayley-Hamilton theorem, this matrix A will satisfy this characteristic equation because it is a square matrix. Every square matrix satisfies its own characteristic equation. So with that, let's start the solution of this very question. So we need to compute determinant of a minus lambda I and equate it to 0. And this implies determinant of, so this is what we are going to use to compute the characteristic equation. A is this matrix, your matrix given to you, 1, 2, 2, negative 1, minus lambda. Lambda is a scalar, while this I is the identity matrix. So since your matrix A is 2 by 2, this I will be 2 by 2 identity matrix. That is a matrix, there is a square diagonal matrix having unit entries. Unit entries are the principal diagonal. You know diagonal matrix now. That's a matrix that has outside the principal diagonal you have 0, but you have at least one non-zero number at the principal diagonal. But for identity matrix, you must have a unit entry throughout the principal diagonal. Then after the principal diagonal, you have 0. That is a square diagonal matrix having a unit entry throughout the principal diagonal. So let's continue. This implies 1 to 2, negative 1. So lambda multiplied by 1, we have what? Lambda. Lambda multiplied by 1, we have lambda. Lambda multiplied by 0, we have 0. Lambda multiplied by 0, 0. Lambda multiplied by 1, lambda. Then determinant equated to 0. So this implies determinant of, let's subtract 1 minus lambda, 1 minus lambda, 2 minus 0, 2, 2 minus 0, 2, negative 1 minus lambda, negative 1 minus lambda, then determinant equated to 0. So this implies, let's compute this determinant of this 2 by 2 matrix. How do you do that? Multiply the principal diagonal first. That's this 1 minus lambda multiplied by negative 1 minus lambda. Then you subtract the product of the other diagonal. 2 multiplied by 2, 4, equated to 0. So this implies, let's expand, 1 multiplied by negative 1, negative 1, 1 multiplied by negative lambda, negative lambda, negative lambda multiplied by negative 1, positive lambda, negative lambda multiplied by negative lambda, positive lambda squared, minus 4, equated to 0. So this implies negative lambda plus positive lambda, you have 0. Then we have lambda squared. Then adding the constants, negative 1, negative 4, we have negative 5. Then equated to 0. This is the characteristic equation. Then by Cayley-Hamilton theorem, this matrix A will satisfy this characteristic equation. So if you plug in A for lambda, this will be equated to 0, right? So you replace this lambda with matrix A. So you have A squared minus, but you have a constant here. Since you have A squared, square of any matrix will give you another matrix, and we want to subtract this constant from it. We cannot subtract a constant from a matrix, so the only solution to this is to multiply it by the identity matrix. Instead of 5, we have 5i, then equated to 0. So we can call this one equation 1. So we need a raised to power 4. How do you do that? We know that if you multiply this a squared by another a squared, we have a power 4 appearing in the equation. So let's do that. Let's multiply equation 1 by a raised to power what? 2. So this implies a raised to power 2 multiply a raised to power 2, we have a raised to power 4 minus 5i multiplied by a raised to power 2, we have 5 a raised to power 2 equated to what? 0. So this implies, let's make a raised to power 4 the solution to the formula. We have a raised to power 4. Moving negative 5a squared to the right, we have positive 5a squared. We can call this one equation 3. So from equation 1, we can get what a squared is, right? Because we need this a squared. If you go to equation 1, we can get it. So from 1, we a raised to power 2 minus 5i equated to 0 implies, let's make a raised to power 2 the solution to the formula. A raised to power 2 will be equal to, moving negative 5i to the right, we have positive 5i. So we can call this one equation 3. So this first one, let's just name this one equation 2. This one will be equation 3. So what we are going to do is, let's create space here. Let's create space. What we are going to do is, we are going to substitute this equation 3 in equation 4. Because equation 4 is saying a raised to power 4 equals 5a squared. So from equation 1, we have gotten that a squared is 5i. So let's just substitute, right? So substitute equation 3 in equation what? 2. So this implies a raised to power 4 will be equal to 5 multiplied by a raised to power 2 gave us what? A raised to power 2, we solved it from equation 1, we got 5i. That's 5i. So this will be equal to, if you multiply, you have 25i. So 5 multiplied by 5i, we have 25i. So this will be equal to 25 what? I is this 2 by 2 identity matrix. And this will give you what? If you multiply 25 multiplied by 1, 25. 25 multiplied by 0 is 0. 25 multiplied by 0 is 0. 25 multiplied by 1 is 25. So this is what we got. So you can verify it on your own to see whether this matrix we have, whether this matrix, that's this matrix 1, negative 1, 2, 2. This was our matrix, right? Matrix A. Check whether, if raise it to power 4 and check, that is multiply it by itself 4 times and check whether you are going to get this quantity. So you can verify that. Okay, this is one of the application of what? Cayley-Hamilton theorem. In our previous video, we saw another application. Which is finding the inverse of a square matrix. And this one is, we can use this to find the certain power of a square matrix. So thank you so much for being part of this video. See you in our next class.